Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad bin SUPAIMAN. My metric number is AA191999 and I'm from section 1 for the subject control system DAE 32103. Okay, so for the first one is the advantages on and disadvantages of the AD controller. So for the advantages, first, it only act on the error, which means it's only act on the error between the desired signal and the control signal. So this situation means that it does not need any extra measurement for the internal state. So this is the biggest advantages of the AD controller. So this is the biggest advantages because when there is extra measurement, so it means that there are more sensor, there are more signal conditioning and more maintenance and also extra cost. For the next advantages is it is easy to be implemented. So PID controller is easy to be implemented, such as in a hardware, which through the filter, and also easy to be implemented through the microcontroller and programmable logic controller PLC. So this controller is easy to be implemented because it does not need any fancy code to design for this controller. So this means that this controller can be written only by a middle level programmer instead of an expert one. Okay, so for the disadvantages, first, it is not suitable for the nonlinear plant. So this PID controller is not suitable for the nonlinear plant, either in general or layman language. Okay, so layman language is the simple language. Okay, so this controller maybe will not assure the desired performance that has been set for the changing environment. So for example, in the application like the submarine, so this controller are just fulfilling the stable performance around the fixed operating region. Okay, so last but not least, for the disadvantages is it is an expensive PI controller. Maybe we see that this controller is enough controller, but it is the expensive one. So this controller will be only used when the process is require the accuracy and also the stability from the PID controller. So the controller will be not take any action until it receives a disturbance and error is occurred. So this matter will cause the recovery time be quite long, resulting in the poor performance. Okay, so for the next one is why PID controller is used. So as we can see, this PID controller has been used in many industrial processes. So first, why PID controller is used is because it has a good ability in handling wide range control problem in the entire process. So this means that this control process has their main mission, which to force the variable to achieve the set point either fast or late. So the actuator will also responsible in executing the controller's corrective effort to make the set point achievable. So by this controller will be the most accurate and also be a stable controller. So last but not least, for the reason is it can easier our task. So this thing is because of the automatic controller or auto tune in the PID controller. So for instance, in the industry that controlling the temperature of water, so to keep constant temperature of the water, the operator just need to set the set point of the water temperature into the PID controller. So instead of using manual operator, they just need to set the set point to set the constant temperature. So by doing this can reduce the workmanship to the operator. So for the third one is the application of PID controller. So as we know, this PID controller is used in the most automatic process control application, either in industry or domestic, so such as to regulate the flow, the temperature, the pressure, the level, and many process variables. So first application of PID controller in the industry is controlling the temperature of furnace. So in general, we know that in furnace it holds a huge amount of raw material. So this material will be not change their temperature quickly. So this condition can be solved by using this PID controller, which we set the temperature that we need, and then it will hit the temperature of the furnace. Okay, so for the next one is it is used to controlling the robotic arm in the industry. So this robotic arm is consists of 4 joints, which is the turntable, the bicep, the forearm, and also the wrist. And all those joints is moved by the servo motor. Okay, so all these joints have their own PID loop and calculated separately. So the proportional determine the reaction to the current error. The integral is used to determine the reaction of the sum of recently appeared error, and the last one is the derivative to determine the reaction of the rate of error changes. So as result, these 3 parts will be contribute to control the mechanism, such as the speed control of the motor for moving the arm. Last but not least, for the domestic, which is such as in our home, PID controller is applied in the house thermostat. So this thermostat is most effective if we are using the PID controller. So if the PID controller is tuned properly, so it can balance the disturbance and bring the process temperature to reach the set point. So but this controller will reduce the power as the temperature approach to the set point to prevent the overshoot and also damage the thermostat, which is due to the too much heat. Okay, so for the last one of introduction is other type of controller. So in this world, so there are many type of controller rather than the PID controller. So one of example of controller is the programmable logic controller, which is PLC. So this PLC is an industrial computer that continuously monitor the state of input device and also make a decision based on the custom program that has been programmed. So any machine function, production line, or a process can be upgraded by using this type of control system. So this PLC has an ability to change and replicate the operation for the process while it communicating to and importing information. So in this controller, it is a modular type, which means you can do mix and match the type of the input and the output device to make it suit with your application. Okay, so for the operation of the PLC, it has 4 basic steps in controlling the PLC, which first the input scan, which the input scan will detect the state of the all input device that connected to the PLC. So the second one is the program scan, which this program scan is act as the execute the program logic that created by the user. Okay, so for the third one is the output scan. So the output scan is the step is energize and de-energize all the output device that are connected to the PLC. And the last one is the housekeeping. The housekeeping, which in this step is it include the communication with the programming terminal, the integral diagnostic, and others. So these 4 basic steps will be continuously repeated. Okay, so it will operate in repeated loop. So example for the some of the application that use PLC is such as the washing machine, the controller, the traffic light, and also the elevator for the general. So for the industry, it used in the filling machine, which in the food industry, the glass industry, and also in the cement manufacturing. So using this application, once it is programmed, this PLC will be will perform a sequence of events triggered by the input. So it will receive a stimuli, and through the delay action such as the time delay.
So let's try run for the transfer function. Number 1 with no PID controller, just original closed loop control system. So the system show that it is unstable system or marginally stable system, and thus it will not have a settling time because the system will not settle down, and also will not have a steady state error because it is unstable system, but it have a overshoot of 95.8%. So let's try them for the original closed loop control system with the PID for transfer function number 2. So the graph show that the system is a stable system. You can call this a system is a underdamped system. So for the overshoot of the system is 69.3%, and for settling time it will be settled. The system is settled at here, which is 11.788 seconds. And for the steady state error percentage, it will be 0 because the system has settled down at our desired value, which is 1.
Hi, Assalamualaikum. Okay, so now we move to the transfer function number 3, which is 7 over s cubed plus 3s squared plus 2s. So now this is the system okay, the block diagram of the system by using Simulink. So before we run the system, we need to set the parameters into 0 except for the final value, which is 1. So after we done that, we just simply run the system. So after that, this is the output graph that we got from this transfer function. As you can see here, it is increased over time. So the overshoot percentage is infinity, which is it has the big value, okay, huge value of overshoot percentage because it increased over time. Okay, the setting time, we have no setting time here, okay, in this graph, and also no steady state error because this system is not stable.
Assalamualaikum. Now I'm going to show for the state transfer function, that is step response for transfer function number 3. So for the step response transfer function number 3, this is the graph, and from the graph we can see that there are two lines, that is step 1 and this transfer function 1. So from here we can see that the graph is the graph response show that the system is a stable system, but it have a huge steady state error problem, and this is the total of our steady state error in the graph. And for the transfer function, this is quite unstable.
Let's continue for transfer function number 1, 2, and 3, and 4 for P control closed loop control system. So proportional control for transfer function number 1, I use a 0.3 value for Kp, and Ki and Kd is 0. So let's try run. So these are the result for transfer function number 1. It is a unstable system. We call it as a marginally stable system, and it do not have a settling time, and also not having a steady state error because the system is unstable. And for the overshoot, it have a 96.2%. So for the next one, I use a 0.4 for value of Kp for transfer function number 1. So let's try run. So for the result for transfer function number 1 with 0.4 for Kp value, the system show that the system is unstable system and marginally stable system, and it did not have a settling down, and also not having a steady state error. Thus they have a overshoot here with value of 99.6%. So for the last value for Kp for transfer function number 1 is 0.5. So let's run. So these are the result from transfer function for number 1 with gain of 0.5, which is Kp. The system show that the graph show that this system is unstable system and do not have a steady state error, and also not have a settling time because it not settled down. But it have an overshoot, which is 93.6%. So we can conclude that the first transfer function, which is use of Kp, is not acceptable for this system to get a stable system. So let's continue for transfer function for number 2 with the value of Kp is 0.1. Let's try run. So these are the result from transfer function number 1 with the transfer function number 2 with the gain of Kp with 0.1 values. So the graph show that the system is stable system because it have a 0% for steady state error, but it have a overshoot of 34.6%, and also having a long rise time here. And then for the settling time, I use a 2% margin for the system to find the margin. So the settling time is at right here. Right here. So so the settling time for the transfer function for number 2 with a gain of 0.01 is 11.782 seconds. So let's continue for the transfer function number 2 with a gain of 0.2. So that's run. So these are the results for transfer function number 2 with a gain of 0.2. So the graph shows that the system is stable system with a 0 steady state error, and also have a overshoot with a 48.5%, and have a short rise time compared to the previous one, which is transfer function number 2 with a gain of 0.1. And also for the settling time, I use a 2% margin. So let's try. So these are the settling time for the transfer function number 2 with a 0.2 gain. So the settling time is a 12.582 second. Just it leads about 1 second from the previous one, which is the transfer function number 2 with 0.1 gain kp. So let's continue for the transfer function number 2 with a gain of 0.3. So let's try run. So these are the results for transfer function number 2 with a gain kp with 0.3. So the graph shows that the system is stable system with a 0% of steady state error, and also having a overshoot higher than previous one, which is it is a 55.2% for overshoot. And for the settling time, so these are the settling time for transfer function number 2 with a gain of kp 0.3. So the settling time is 12.16 seconds. So we can conclude that the system for transfer function number 2 is a stable system, but it have a problem with the oscillating part because it takes a long time to settle down the system. Besides, it have a huge overshoot when the gain of kp start increase. So the system should apply a pi or pd in order to get the perfect form of stable system. So let's continue for transfer function number 3. For gain kp, I use 100 and 200 and 300. So let's try 100 first. So these are the results for transfer function number 3 with a gain of kp 100. So the graph shows that the system do not have a overshoot because the peak of the system not go beyond our desired value, which is 1. So there's no overshoot. Then the system have a huge oscillating here, and they settle down at the value of 0.33. So to find the settling time, we have to use a margin of 2%. So 0.33 will be 0.35. So let's see. So the settling time for the system is 2.087 exactly. Then for the steady state error, the value that is settled down for the stable is 0.33. So 0.33 minus with 1, we will get about 66.7%, which is 0.667. So let's continue for transfer function number 3 with a gain of KP about 200. So these are the result for transfer function number 3 with a gain of KP 200. So the graph shows that it is a stable system. It's settled down at 0.5, and also it still do not have a overshoot yet, but it still have a settling time because the system is settled down. So let's try to find the settling time first. Because of using a 2% margin to find the settling time, so the settling time for transfer function 3 with the gain of KP 200 will be 2.542 seconds, just at here. Then we have to find the steady state error, which is the system settled down at 0.5. So 0.5 just minus with 1, which is our desired value, and then multiply with 100. So we will get 50% for steady state error. So the last one will be 300 value of KP for transfer function for number 3. So let's try run. So these are the result for the transfer function number 3 by using gain KP of 300. So the graph shows that it have a overshoot, but the system is stable system. So the overshoot of this system will be 6.2%, just overshoot. Then for the settling time, it will be 2.645 seconds for the settling time of the system. This is because I'm using a 2% margin. Therefore, it will be 0.62 and 0.58. So for the steady state error, we just minus with 1 with 0.6 because the system has settled down with at 0.6 value. So the steady state error of the system will be 40%. So we can conclude that for transfer function number 3, it needs a PI and PD to get a more stable system, because this system for transfer function number 3 with the using of P only, which is proportional. The system have a problem with the steady state error, and also have a problem with the overshoot when we increasing the number of gain. So by using the PI and PD or PID, the system maybe will be more stable than we using of P for transfer function with number 3. So let's continue for our last transfer function, which is transfer function number 4. So I use a 0.1, 0.2 and 0.3 for proportional gain. So let's try run. So these are the response for the transfer function number 4 by using 0.1 gain of KP. So the system shows that it is a stable system. However, it have a huge problem for the rise time because it takes a long time to rise. Then for the overshoot, it will be 5.5%. And then for the settling time, I use a 2% margin. So I got 11.24 seconds at here. Then for the steady state error, it will be 0 because the system are stable. So let's continue for the transfer function number 4 with the gain of KP by 0.2. So let's try. So these are the response for transfer function number 4 by using the KP value of 0.2. So the graph shows that the overshoot of the system is 25.3%, which is higher than the previous one. Then for the settling time, use a 2% margin. So the settling time of the system is 11.452 seconds. Then for the steady state error, it will be 0 because the system settled down with the our desired value, which is 1. Then for the rise time, it is faster than the previous one. So for transfer function number 4, which is our last transfer function for proportional gain of 0.3 value. So let's try run. These are the result for the transfer function number 4 by using the gain of KP 0.3 value. So this system shows that it is a stable system with a overshoot of 40.9%, and also for the settling time, I got 11.24 and I got 15.835 seconds, and also for the margin I use a 2% margin. Then for the steady state error, it will be 0 because it settled down with our desired value, just 1. And then for the rise time, it is faster than previous one. So for this, we can conclude that transfer function number 4, we can conclude that the system need a PI and PD to reduce the overshoot of the system and to reduce the oscillating of the system, because we want to get a system that faster in terms of rise time, and also not having an overshoot, and have a steady state and not having a steady state error, and also have a short settling time.
Okay, we move to the question number 7, which is we need to set the KP value. Choose the best value out of 3 values that has been submitted in step 6. Set KI to 0, vary the derivative coefficient. KD, try 3 different KD values. Observe, record, and predict the overshoot percentage, setting time, and steady state error. So this is the transfer function number 1. Okay, this is the table that we get from question number 6. This is the 3 different KP value. So out of these 3, I think the best is 0.3 because it has the smaller value of overshoot percentage. So the testing value of KD here is 0.13, 0.23, and 0.33. So we move to the KD when KD is 0.13. Okay, this is the KD 0.13. It has overshoot, settling time on, and it has no steady state error. Okay, the setting time is 1.2 and the overshoot is 28.5. Okay, when KD is 0.23, okay, we see that it has a bit of overshoot, and it is in the stable graph. It means that the steady state error is on the final value. So the setting time is 1.75 and the overshoot is 5.8. So when KD is 0.33, okay, it has no overshoot. Okay, it is the stable graph. Settling time is 3.5. Overshoot, it has no overshoot, 0%. So we move to the transfer function number 2. Okay, out of these 3 KP values, I think the best one is 0.1 because it has the smaller value of overshoot percentage, and also the setting time. Okay, the testing value of this KD is 0.1, 0.2, and 0.3. Okay, when KD is 0.1, okay, we see that no overshoot. It is in the stable graph, which is the steady state error is 0%, and the setting time is 4.23. When KD is 0.2, okay, we see that the settling time is increased, which is 9.51, and has no overshoot and also no steady state error. When KD is 3, okay, we see that settling time is much bigger, which is 13.34, and it has no overshoot and also no steady state error. Okay, we move to the transfer function number 3. Alright, out of these 3 KP values, the best one is 300 because it has the smaller steady state error, which is 40%. So the testing value of KD here is 100, 200, and 300. Okay, when KD is equal to 100. Okay, this is the graph. This is the graph that we get. Okay, it has settling time, there's no settling time, and steady state error is bigger, which is 40%. Okay, move to the KD when KD is equal to 200, right? Like before, we have this graph, but it did not reach to the final value, which is 1. So the steady state error here is 40% also. Okay, we move to the KD when KD is 300. Alright, we got the same value, same graph from before, and it's also have the same steady state error 40%, but it can be solved by implement the integral coefficient in PID system. Now we move to the transfer function number 4. Right, out of these 3 different KP values, the best one is 0.1 because it has a much smaller value of overshoot percentage. So the testing value of KD here is 0.001, 0.002 and 0.003. Okay, when KD is 0.001, right, we see that it has a small overshoot here, but it has no steady state error. So the setting time here is 10.7 and the overshoot is 5.8. Okay, when KD is 0.002, okay, like before we have the small overshoot here, but it is in steady, it is in stable graph, okay, stable system, and the setting time here is much bigger from before, which is 11.7 and overshoot is 5.4. Okay, this is the last one, KD when KD is equal to 0.003. Okay, like before we have the small overshoot here, but it is in the no steady state error here. Okay, which is settling time is 11.6 and overshoot is 5.1%. Right, I think that's all from me.
ASRAFF and JAMILUS, and I'm going to show the result for the PID, where there is the value on the KP, KD and KI. So for the first result, it's going to be the transfer function 1, and the result we're going to use for KP, we're going to use 0.3, and for the KD 0.23. So next, we're just gonna use 0.00001 and until 0.0003. They're gonna get our overshoot is the same, 6.6, and setting time gonna be a bit different, just a bit, 1.6, 1.65, 1.67, and there's not gonna be steady state error. And this is the graph for the first one, is 0.00001, and this is the graph. Then next one gonna be 0.00002, and next gonna be 0.0002803. Okay, next is gonna be the second transfer function, that and gonna use KP. The value of KP gonna be 0.1 and KD gonna be 0.12 and KI gonna be 0.00001, and so on, like the transfer function 1. And for this is not gonna be any overshoot, and they're gonna be shoot time and no steady error. And this is the graph for the first one, 0.0001. And this is for 0 this is for 0.0002, and this is for the last one, 0.00003. For the third one, gonna be transfer function 3. For the KP value, we're gonna use 300, and the KD value we're gonna use 100, and for the KI value we're gonna use 1000. And we're gonna test it with, we're gonna have 3 value
three answer so that we can have the most suitable overshoot and settling time. So we're gonna use 1000, 1050, 1500 and 2000. Overshoot we're gonna get 5.4. Settling time gonna be 0.16, and this is the graph. And next gonna be the 1500. The overshoot is gonna be 12.1, and the settling time will be 0.43. Then this is the graph. For the last one gonna be the 2000, 70.4 for the overshoot, and settling time 0.36. This one. And for the last transfer function, we're gonna go with KP gonna be 0.1 and the KD gonna be 0.001. And for the KI, we're gonna go with 0.00001, and we can do it until 0.0003. And for the first one, 0.0001, the overshoot is gonna be 55.8, and settling time gonna be 10.7. Yes. And next one, go with 0.0002, the 5.4, 11.7, and no steady state error. This is the graph. This is the last graph, and we're gonna get overshoot 5.5, and the settling time gonna be 11.165.
Assalamualaikum warahmatullahi wabarakatuh. My name is KHAIRUL NAZMI bin MOHAMAD. Today I'm going to be presenting about the conclusion for our control system project. So firstly, what is a PID controller? PID controller is a proportional integral derivative controller. PID controller or three-term controller is a control loop mechanism. PID controller calculates error value ET as the difference between the desired set point SP, the calculated variable PV, and applies the correction based on PID terms. Next, in this project, we are given 4 transfer functions. The transfer functions are as shown below. So these are the transfer functions that are given to us that we need to simulate in MATLAB. So conclude the effects of PID coefficient for each transfer function. For transfer function 1, P controller increases the value of overshoot and no change in the settling time, and steady state error. I controller decreases the value of overshoot and settling time, also eliminates steady state error. D decreases the value of overshoot and settling time, and also eliminates steady state error. Meanwhile, for transfer function 2, P controller will increase the value of overshoot and settling time. Also, it will eliminate steady state error. I controller will eliminate overshoot and steady state error, and it will also decrease settling time. The D controller in transfer function 2 will eliminate overshoot and steady state error, also decreasing the settling time. Next is for transfer function 3. P controller increases the overshoot and reduces the settling time, small change, and also decreases the steady state error. I controller will eliminate overshoot and steady state error, also decreases the settling time. D controller decreases overshoot and settling time, also no change for steady state error. Last but not least, for transfer function 4, P controller has no change in overshoot, settling time, and steady state error value. I controller eliminates overshoot and steady state error, also decreasing the settling time. Meanwhile, D controller will decrease overshoot, settling time, and steady state error. Okay, next is conclude which controller performs the best for each transfer function. Transfer function 1, the output of the system is shown below. This is the graph. What we can conclude here is that the best controller for this transfer function is PD controller. By using PD controller, the output of this system will get 0 steady state error and less percentages of overshooting. Next is transfer function 2. The output system is shown below. This is the output graph. What we can conclude from this is the best controller for this transfer function is also PD controller. The reason is that by using PD controller, the output system will get 0 steady state error and 0 overshoot. Next is transfer function 3. For the third transfer function, the output system that we obtain is shown below. From this, we can conclude that the best controller for this transfer function is the PID controller. This is because when we use PID controller, the steady state error and the overshoot value of the output will be 0. Last but not least, for transfer function 4, the output that we obtain is as shown below. Based on this graph, we can conclude that the best controller for this transfer function, is the PD controller. The reason is that by using PD controller, the output of this system will have less percentages of steady state error and less percentages of overshooting. That is all from me. Thank you.